NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How is everyone tonight? Good. Well, thank you very much for coming out. It's nice and cool in here at least, right? So anyway, shall we? With thousands of planets now known around other stars, it's natural to wonder why so many planetary systems are quite different from our own. Some stars have several planets inside the location of Mercury's orbit, where our solar system is basically empty, while other stars have planets more massive than our Jupiter on looping eccentric orbits. A few stars have hot Jupiters circling every few days on orbits so tight the starlight heats the planet's atmospheres beyond the point where iron vaporizes. And many stars have planets intermediate in size between our rocky Earth and icy Uranus, sizes that are completely missing from our solar system. And some planets orbit not one, but two stars. So where did all this diversity come from? We know planets must form from the dust and gas orbiting young stars because we see the orbiting material with the Hubble and Spitzer telescopes and ground-based telescopes. But the dust makes the material opaque at optical and infrared wavelengths, so it's hard to know what's going on inside. In recent years, our view has become clear enough to make out some features that might be caused by young planets orbiting within the material. Tonight's guest will discuss several of the new images and a few of the 3D computer models astronomers are using to try to learn how planets are born into such diversity. Tonight's guest grew up in Australia, where as a teenager, he built a small telescope that he used to study the Milky Way and comets. He earned a bachelor's degree at the University of Sydney, then moved to the US for a PhD in astrophysics at UC Santa Cruz. And after his stints at the University of Maryland and UC Santa Barbara, he came to JPL, where he now supervises the interstellar and heliospheric physics group. For him, a typical workday involves building computer programs to compare models of what happens during planet formation with the observations sent back by space telescopes. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Neal Turner.
Hello and welcome. I guess the mic is on. So I would like to share with you the story of what we know so far about planets around other stars. In the last 20 years, thousands of planets have been discovered at an increasing rate. Only the few brightest are directly imaged, like this one here. So the star's been mostly removed in the center, and then the three little dots, B, C, and D, are the three planets here. But these are unusual. They're particularly large and bright and particularly far from their star. In most cases, we cannot see these thousands of planets directly. Most were found by two methods, either using the motions of the stars in response to the planet. So this movie shows a star here and a planet going around it, and you can see that although the planet is going around the star is also, in a sense, going around the planet. It moves a little in response to the planet's gravity. And that means that the bright star, we can just look at it and see its motion towards us and away from us. And in the same way that when a fire engine comes toward you, its pitch gets higher, and then as it goes away, the pitch gets lower. Same thing happens with the star's light. So we can see a bluening as it comes towards us and a reddening as it goes away. So we can use this radial velocity method that's been used to discover many of the new planets. The other main way is through transits. And that basically is just a fancy way of saying that the planet goes in front of the star and blocks out a little bit of its light. So the biggest planet in our own solar system, Jupiter, is about 1/10 as big across as the Sun, which means 1/10 in each direction means about 1/100th total of the Sun's light would be blocked if Jupiter were to pass across its face as seen by somebody very far away. And so most of the planets that have been discovered have been found by this method using the Kepler Space Telescope, which studies a large number of stars looking for the slight dimming when a planet goes in front. As better telescopes have been built, and also as we've gotten better at analyzing the results from the telescopes, at teasing out the little signals that we get from the planets, the masses of the planets that we can see have gone down. So this shows years, the year in which each planet was discovered. So the first one that everybody believed was about 1995 here. And as a function of the mass, so Jupiter is here, Neptune, and the Earth. And you can see that as techniques have gotten better, the lowest mass that we can detect has gone down and down. And now it's at about the mass of the Earth. So it's an exciting time to be part of this search for new planets. By the way, gray is the radial velocities and red is the transits. And so you can see that when the Kepler telescope was launched into space in 2009, the red dots really take off. So many more planets have been discovered. It's also an exciting time because thousands more of the planets are going to be discovered in the next few years. So a couple of years ago, the European Space Agency launched Gaia, which measures the positions of the stars very accurately. And so as the planet goes around, once again, you can see the star's motion, but this time in the plane of the sky. And so Gaia should discover several thousand more new planets. And also TESS, which is a super Kepler, with an even bigger fly's eye of telescopes with more megapixels, and it will, because it has that bigger field of view, it can study nearby stars. Kepler had to concentrate on a smaller field far away, but TESS, the Transiting Exoplanet Survey Satellite, will be able to see all of the nearby stars by scanning the sky. So we'll find out about our neighbors, the planets around our neighbor stars. And that's due to launch in a couple of years' time. So tonight I'd like to discuss three questions. First, what are other stars' planets like? And like the other questions, this is one that people have been asking for a long time, and it's great that now we have a chance at last to answer it. And I'd like to share what we know so far about the answer to this question. And the second one is how are they different from the planets around our own sun, which we've known about for thousands of years, and it turns out they are quite different. Many of them are totally unlike anything we've known up to now. And then the third question is, why are they different? That is, what's different about their history, what's different about how they came to be where they are, that has made them so different from our own solar system and so diverse, so different from one another. So on to the first question. So the first planets to be found were what are now called hot Jupiters. And they were first to be found because they're as big and as massive as Jupiter. You can see this one is a good fraction of the diameter of its host star here. So big and heavy means that they make the star move a lot, so that movement is easy to see. And the other thing is that they are very close to their star. Many of them are in orbits of just a few days instead of 365 days like our Earth. And so they're whizzing around the star so often that you just need to look for a few days with a telescope and you'll see that signal repeat. You'll see the star move towards you and then away from you and then towards again. And so because of that quick repetition, they are easy to see. But because they are so close to their stars, they become very hot. They become much hotter than even the innermost planet in our solar system, Mercury. And on their surface, the temperature is hot enough to melt most metals. And so they have to be gas giants, even if some of the gas is metal vapor. And based on the number of these that have been found, they must orbit around 1% of the nearby sun-like stars. So there are a lot of them, but they're still somewhat rare. But they are completely unlike anything in our solar system. The next easiest kind of new planets to find are the eccentric giants. So these may have a mass close to that of Jupiter, but instead of going on a nice, steady circular orbit, they go on big loops. They start out far from their star, they plunge in very close, and they go far out again. This example goes well outside the orbit of Mars, if you were to place it in our solar system, and just inside the orbit of Mercury. And the fact that they're eccentric means that they must have had something violent happen to them in the past to knock them off the orbit where they were initially formed. And the number of these that have been found suggests that they orbit around 5% of the nearby Sun-like stars. Maybe 1 star in 20 has one of these. But then the third kind, the hardest to find but the most numerous, are smaller. And they're on orbits less than about 100 days, because that's what Kepler has been able to detect. This shows a sampling of them. Each little set of circles is one of the planetary systems. The colors just show the order, so red is nearest to the star, yellow is next, and so on. And you can see the relative sizes. So here's a super Jupiter, and there are many smaller planets. And for comparison, up here is our solar system with Mercury, Venus, the Earth, and Mars. And we're going to zoom in because a lot of these systems are really small, very compact. You have, in many cases, several planets orbiting quite close to their star, inside the orbit of Mercury. So, but the bottom line from all of these three classes, new classes of planets, is that if you look up at one of the bright stars in the sky, bright means it's probably nearby, there's about a 50% chance that it has one or more planets, Earth mass or greater. And these numbers are just because this is what we are able to detect so far. There could be more. There could be many more. So the second question I'd like to talk about is how these planets are different from the planets in our own solar system. And this is where it gets interesting because it starts to tie the strangenesses of these new planets to how we perhaps came to be here on Earth. So in our solar system, the innermost planet is Mercury, and its orbit is 88 days long. It's about 4/10 as big across as the orbit of the Earth. Compare that with this one system of planets around another star, the Kepler-11 system, and it has 1, 2, 3, 4, 5 planets inside Mercury's orbit, and then another one in between Mercury and Venus, if you put it in our system. So in our solar system, this region inside here is empty, but in the other system, there are quite a number of planets. And this has been repeated again and again. It's a common pattern among the systems that we've been able to see. So this is a great mystery. Why is our solar system so different from these other systems? Why is our solar system special in some way, or rare? In most other respects, in terms of our place in the galaxy or our galaxy's place in the universe, we are not special, we are just typical. But our solar system does seem to be unusual. In our solar system, so here's everything to scale, the Sun here on the left, we have two big planets, Jupiter and Saturn, both about 10 times the radius of the Earth shown here. We also have two ice giants, ice and gas giants, Uranus and Neptune, which are each about 4 times the diameter of the Earth. And then we have Earth and Venus, which are pretty similar, except that Venus has serious greenhouse effect. And then some smaller stuff, Mercury, Mars, Pluto, and so on. In contrast, around the stars that we've been able to see, where we've been able to see so far, cold, relatively distant giants like Jupiter and Saturn seem to be relatively rare. There are the eccentric giants, but they're quite different because they loop in close to their stars and become warm. Jupiter and Saturn stay out beyond where water can survive. And that, as far as we can tell so far, is rare. But that's just at the limit of our knowledge now. We're just beginning to be able to pick out those cold giants. Another interesting difference between our solar system and these other new ones is that we have nothing in size between the Earth and Uranus and Neptune, which are about 4 times the Earth's diameter. They're very different in composition. The Earth is, of course, mostly rock and metal. Uranus and Neptune have a core inside of rock and metal, and then ice as well, and then some gas, some hydrogen and helium on the outside. But when we look at the population of planets around the other stars, we see something quite different. So here, this is a bar chart, so the average number of planets per star versus the radius of the planet. So for example, about 10% of these stars have planets between the Earth's radius and 1.4 times the Earth's radius. But then the interesting thing is that another 10% have planets with radii between 1.4 and 2 times Earth's radius. And then yet another percent have planets in this next range up. And it's only when we get up to here about 4 that our solar system has another one. So the interesting thing is that we have a couple of planets here, a couple of planets here, and nothing in between. And yet these are the most common among the ones we've been able to find around other stars. So that's a mystery. Why are we different again? Another thing that we can see here is that when we get down to, so Jupiter is about 11 times the Earth's radius, and Saturn is about 9. So they both fall in this bump here. So you can see there's a steep fall off here, and then a less steep fall off, and there's this little bump here. Maybe that's telling us something about how these planets formed. Maybe it's a bit more difficult as you grow, as you try to form bigger and bigger planets. Either it's more difficult to form them, or once they're formed, they quickly grow until they come up to this size, and then they stick there. There's something special about planets like Jupiter and Saturn. We have a little bit more information than just the radius for at least some of these new planets. So for some of them, we can also measure the mass. If we can see the radial velocity, if we can see how the planet is driving its star, then that tells us the mass, in addition to seeing the size from how much of the star's light it blocks. And if we put those two pieces of information together, we can get the density. So here, the planet radius is plotted in Earth radii, the planet mass in Earth masses. So the Earth is right here at 1 and 1, and Venus is just below it. And the other comparison point here with our solar system is Uranus, up at the top right there. About 4 Earth radii and about 14 Earth masses. And you can see that there is a lot in between in this region that is completely unpopulated in our solar system. So each of these colored points is one of the newly discovered planets. We're a little bit uncertain on their masses and a bit less uncertain on their radii, shown by the bars there. And then when you put together a mass and a radius, then you get a density. The interesting thing is that in the top left corner here, these planets have densities less than 1 gram per cubic centimeter, less than water. So if they were small enough, they would float in a bathtub. And that means that they have to be mostly gas in order to get the density that low. If you made them out of Earth rocks, then their mass would increase in this way with radius. If you added some water, if it was half rock and half water, it would follow this curve. If it was all water, it would be on this curve. And many of these planets are up above even all water. So that means they have to have some hydrogen and helium mixed in, shown by the dotted curves there, how much of the hydrogen and helium you need to mix in. So not only do we have planets in this region in between the Earth and Uranus and Neptune in size, but also they're quite different in composition. They're fluffy in a way that even Uranus and Neptune are not. So they're strange beasts, unfamiliar beasts. Oh, I didn't mention yet, the colors of the points show how much light they receive from their star. So this is the flux in units of the flux that the Earth receives from the sun. You can see that many of the colors are yellow or red, indicating that they receive 100, 1,000, or even 10,000 times as much light from their stars, because remember, these are close, because we can most easily see the ones that are on orbits less than 100 days, quite close to their stars. But in another way, many of these extrasolar planets are quite like the solar system. Here's a little map of the solar system as seen from the side. So the sun is here, and the planets are lined up with the planes of their orbits shown by the lines here. And the one that tilts the most out of the plane of all of the rest is Mercury, and it's about 6 degrees. And the others are all less than that, so the numbers are listed down here. Many of them are less than 1 degree. The Earth is only 1.6. So they're basically all lying in one plane, and that's consistent, at any rate, with them all having formed together out of the same material. So they all share, not quite share an orbit, but they have orbits of different sizes in the same plane. And we know that many of the planets around other stars, the systems that have multiple planets, must be like that too, because we see them go in front of the face of their star one by one after the other. And so that means, again, they have to lie very close to the same plane. Otherwise, they would pass above the star or below it, and we would not see those transits. So in this way, the other planets are similar to ours, and perhaps that's saying that in some respects the way they formed is similar too. But some of the hot Jupiters break this rule. This is one that was found with the ground-based telescope, so wide-angle search for planets, I think, is its moniker. And here, this line and the arrows here are showing the star is rotating like this around a vertical axis, and yet the planet is plunging along this line here, up and down around. So it's almost, the plane of its orbit is almost perpendicular to the equator of its star. And this suggests that something violent has happened to push it away from where it used to be. So finally, I'd like to get on to the part that's speculation. And this is what I do for my day job, so I'm very happy to talk about it. So we don't know the whole story of how they're born. We're still trying to piece it together. I'll try to outline a few of the chapters, a few of the things that we think may have happened, even if we don't exactly know the order. So first, around many young stars, we see orbiting clouds of dust and gas like this one. So the star here is hidden. So there's a disk of opaque material around the star, and it happens in this case to be seen edge-on. So we can't see the star directly. Instead, what happens is that some of the dust and gas lies above and below the disk, and that, especially the dust there, reflects the starlight, scatters the starlight towards us. So this light above and below the disk is the material, the low-density material in the outskirts of this cloud, bouncing the starlight so that we can see it. You can see the line is a little bit red here because some of the dust, the denser dust, is absorbing some of the blue light as well. So a typical size for this cloud is about the size of the solar system or a little bit bigger. So that's good because we need to form a planetary system. The mass in it is about enough to form the planets, plus some extra hydrogen and helium. So that's one of the problems that we have to solve. We have to get rid of that extra gas to leave the planets behind. And we can't watch one of these and see how long it lives, because it lives for a few million years, but we can look at star clusters of different ages. We can work out the ages by studying the stars, and we can see that around clusters that are more than a few million years old, almost none of the stars still have these clouds. So from that, we guess, it's an educated guess, that they live for a few million years. So that's the amount of time that we have available to collect together these interstellar, tiny, sub-micron-sized grains of dust, collect them together in their trillions to form planets. Another thing is that if we work out how long it would take for this dust to settle down, for all of this extra dust out here to collapse down and form a thin line in the middle, it's maybe a few thousand years, something in that ballpark. So it's much less than the lifetimes of these clouds. So that means that something has to be keeping the dust stirred up and preventing it from settling. And that something is probably turbulence. And that turbulence has a role to play in forming the planets. From modeling in the computer, we know that if you have a magnetic field, and if the gas is ionized enough so that it can feel the magnetic forces, then the forces drive turbulence. a magnetic field connects material close to the star with material a little bit further away and pushes the further away stuff onto a higher orbit while letting the closer stuff spiral into a lower orbit. Some of it eventually will spiral right in and collapse down onto the surface of the star, so the star will grow a bit. On the other hand, the outer reaches of it are going to spread and the disk will get bigger over time. But all of that relies on having enough ionization so it can couple to magnetic fields, and we don't know whether that is the case. We can even see planet formation beginning. Here is an image from a giant new radio telescope that's still being assembled in the Atacama Desert in South America. It shows the disk around a young star, which is at the center here. And at radio wavelengths, the telescope is sensitive to pebble-sized or sand grain-sized particles, which means they're far bigger than anything in the interstellar medium. So that means at least the very early stages of planet formation have begun inside this protostellar disk. There are rings. You can see that the dust seems to be gathered together, so there are rings and gaps and more rings and more gaps. And astronomers are still debating. This is a new result in the last year. Maybe it's planets, maybe it's the tides of planets orbiting within it. So perhaps a planet has cleared this gap and another one has cleared this gap and so on. But another possibility is that perhaps what's happening instead is that the dust particles are starting to stick together, and they stick together more efficiently in regions where you're near the threshold for vaporizing one of the materials that makes up the ices. Some of these gaps seem to correspond to those locations for evaporating different ices. And yet another possibility is that this material is dense enough to begin, under its own gravity, begin to accumulate together to build up these rings. So you can see that there are lots of possibilities, and we have a lot of work to do to sort out which ones might be right. Once we get beyond that pebble size, we can't see what happens. If you have 1 trillion dust grains floating around, they have a lot of surface area. But if you collect them together into a compact ball, they have much less area, and so they don't emit at all, basically. Their emission is far too feeble for even the best of our telescopes to see them. But it seems likely that planets form easiest a little bit further out than the Earth. At the Earth's location, it's a bit too hot for water ice to survive, as you can tell from seeing that comets, when they pass the Earth's orbit, begin to evaporate. But if you go a bit further out, you still have quite a lot of material, and yet the water can survive. This picture is taking it to the extreme. This is an artist's impression of the surface of Pluto, and the sun is so far away that it's just a bright star, and that's why Pluto is so cold. And for the same reason, the outer reaches of the early solar system are a good place to build planets, because you have a lot of ices. And if you take the ice and add it to the rock, then you triple or quadruple the amount of solid material that you have available. So that helps in many ways to speed up the building of planets. But if we form the planets in the outer solar system, why are there so many of these planets around other stars close in? It seems to require moving house. The young planet has to up and pack its bags and somehow move close in to the sun where it's hot. One possibility is that they migrate inwards by interacting with the gas around them. So here's a movie from another computer simulation, and to look at things in detail, even on the big computers that we have today, we have to look at a small patch. So our camera here is staying fixed on the planet as it orbits around the star. You can see that material on the left side of the screen here is orbiting faster, so it moves up relative to the planet. Material on the right side of the screen is orbiting slower because it's further from the star, so it appears to move down relative to the planet. And you can see that despite the turbulence that makes this calculation messy, there's a spiral arm pattern here. So material that approaches the planet from below, going faster, it gets pulled a little bit towards the planet. And that deflection means that there's extra material in this spiral arm downstream. Same thing happens on the other side for material that's lagging behind the planet. Once it's attracted to the planet, it then collects into this spiral arm on the other side. And each spiral arm exerts a force on the planet through its gravity, but the forces aren't quite the same. Typically, the arm on the outside exerts a slightly bigger force, and that means that the planet is gradually going to drift in towards the star. Over time, it could approach the star very closely. So this may be a good way to make those tightly packed systems of planets. There's another way to get the planets in close, which works at least for the hot Jupiters, and it involves tides, just like the tides on the Earth. So if we have a distant Jupiter, it encounters another of its kind, so it's scattered onto an eccentric orbit, so it's looping in close to the Sun and out again, back to near where it started. But when it's in close, its gravity raises tides on its star. And just as tides on the Earth get dissipated by moving around the land masses, tides in the star also get dissipated. The star gets a little bit of extra heat from that, and the planet's orbit, the outer end of its orbit, grows shorter and shorter. And it can eventually end up in a close orbit in tight around its star. So here's what the tides do on Earth. You can see it's easy to get out to the lighthouse at low tide and not at high tide. So twice per rotation of the Earth, the gravity of the moon is pulling the ocean up, and the same thing happens on the star. Twice per rotation of the star, the gravity of its planet will pull the tides up, and then the tides will dissipate into heat that removes energy from the orbit. So this is a second way that we could make at least the hot Jupiters be close to their stars. So I see that I've come almost to the end already, so I have plenty of time for questions. These are the questions that we haven't answered but would like to. These are the things that we're focusing on for the future. First, how did the planetary systems come to be so different from one another? We've seen that some systems have hot Jupiters and relatively few other planets. The hot Jupiters seem to be accompanied by fewer companions than other systems. We've seen other systems have the eccentric giants, where there's a big body that plunges through the inner parts of the planetary system and out again. So they must have had some kind of violent event in their past. Why do some systems have those violent happenings and others do not? And we've seen that yet other systems have several planets packed in close around their star, where our solar system has basically nothing. And so what's different about the history of our solar system? We have 4 cold giants also on orbits that are nearly circular, and that seems to be unusual. What's special about our solar system? Were we lucky in a way that we didn't have a violent event in the outer reaches, and yet unlucky in that something special happened close in to the sun? We don't know. It's still to be investigated. And finally, working towards finding other Earths, we'd like to know what the ones that we can see so far, the ones that are just a little bit bigger than the Earth, what they are made of, and then how were they put together? Why do some of them have that fluffy composition? Why are they gas to a far bigger extent than the Earth? And are any of them truly Earth-like? Can we find any that are rocky and yet they do have an atmosphere that we might recognize similar to our own? So I'll put back up my starting slide. And maybe I can say also, I talked about migration for the giant planets, but for the small rocky planets, we'd like to know how they migrate too. This artist's impression is showing what happens when you have some rocky material in close to the star. I think the evidence from the fact that so many of those small planets are coplanar suggests that they must have undergone migration too. I think that that's probably the common thread, because in our solar system, all the planets share a plane. In those other systems, they do too. And so it has to be that they formed through a common process. So I've come to the end, so I'll be very grateful to take any of your questions. I've been told to remind you to come up to the microphone, please, to ask questions. So that way our viewers online can hear the questions as well.
My question is regarding the tides that between the sun and the planet that I believe you mentioned is possibly responsible for bringing the planets closer to the sun.
Yes.
And I'm wondering about the difference between that scenario and the tide between the moon and the earth, where the earth's rotation has been slowed due to the relationship between the earth and the moon actually goes further out. So I'm wondering about if there's a difference or what's going on there.
It's similar, but just a little bit different. So in that case, because the Earth rotates in 1 day, whereas the Moon orbits in 30 days or so, and that means that the bulge that the Moon raises in the Earth gets a little bit ahead of the Moon's location in its orbit, and it pulls on the Moon and accelerates it forward, and that's why the Moon tends to move further away. But that's not guaranteed to happen in exoplanet systems. So, for example, you could have a situation, as we actually have with Mars and its 2 small moons, where they're orbiting inside the point where they would be going around once per day. So they actually orbit faster, and so they're pulled back by the bulge on the planet, and so they will eventually crash into the surface.
I see. Thank you.
Yes, I was wondering how many main sequence objects you found in your new study of new planets. And also, is it possible that the stars could migrate through nuclear fusion?
I guess I'd like to understand a little bit more about your question. So it is certainly true that as stars use up the fuel in their insides, they tend to expand generally as they move through their main sequence lifetime. And things could get interesting if you have a hot Jupiter and one of those stars expands enough so that it approaches the Jupiter's orbit. And it could be that the planet gets swallowed up. We haven't seen anything like that yet, as far as I know, and that's probably because the swallowing up happens quickly. Once the planet is in even the low-density upper layers of the star, it very quickly spirals down and is lost. So we would probably have to look at a lot of stars until we could get lucky enough to see that happen.
Is it possible, though, that the geothermal process could add to the collapse of the star from the core?
Well, even a Jupiter has only about 1/1000th of the mass of a Sun-like star. And so from that point of view, it would only be a small perturbation. It does add a little bit of extra heavy elements, but they are probably deposited in the outer layers, and so they would have only a small effect on the star's own gravity and probably little effect on what's happening right at the core where the nuclear fusion is ongoing. But it might be detectable. So there are some people that suggest that stars with planets may be a little bit enriched in heavy elements, for example, in their surface layers.
Thank you.
Hi, this is a 3-part question. I was wondering if you can give us examples of the type of violent events that would have impacted the planets as they formed. The second question is, would those events occur while the planets are forming or after? And have we been able to observe any violent events with planets that we're looking at now? Yeah, that's the third question.
So, similar to in the last question, so because they're violent, they tend to be over quickly. And so mostly we see the aftermath. We see the planets that are on unusual orbits. So to give a concrete example, so some years ago, actually 20 years ago now, there was a comet that crashed into Jupiter. And that was a violent event. It happened over just a few years that it happened to have a close encounter and get captured by the planet. And then it went into Jupiter, crashed into the atmosphere fairly quickly. And for a similar reason, we would have to get quite lucky to see one of these violent events. The violent events, they would probably involve a close passage. So in the solar system, the planets are mutually stable. They don't interfere with one another terribly much, but only just. So if you were to move Jupiter or Saturn just a little bit towards each other, then you could have them interact enough that they would have bigger and bigger disturbances and eventually have some very close passage and then go on to completely new orbits. And that's the kind of violent event that may have shaped some of these extrasolar planetary systems. But we just have to infer it from computer models and from seeing the debris, basically, that's left over afterwards.
Thank you.
So my question relates to the fact that you made a number of claims based on that our solar system is unique from others. I was curious, is that uniqueness basically based on us only being able to see certain types of other planets? Or put another way, do you think as our search methods are refined, we'll find a larger percentage of solar systems like our own?
My fear is that we don't know enough yet. So in particular, so just in the last couple of years, we've been able to begin seeing Earths, and we're just now being able to see the cold giants. So in a few years' time, I hope that the picture that I've given you today will be still correct, at least as far as the close-in planets. But those outer ones, our knowledge is much less certain, and so the picture could change. So for example, there's another method, a new method called microlensing. When a star and its planet go in front of a background star, the background star gets lensed, so the light gets focused on us, and it gets a little bit brighter, and we can see a extra brightening for the planet. And through that method, we can detect planets that are further out from their star, even if we can only see them just that one time that they go in front of the background object. And so through that method, a few planets have now been found that are cold giants. And so if a lot of those are found, then that part of the picture I've described could change.
Thank you.
I have a question about one of your graphs. You had an XY graph that showed mass and size.
Yes?
And I just wondered, you pointed out an open area in the upper left, but what happens at the bottom of that chart? Is it because we can't visualize planets that are smaller at this time?
That's right. So to give a feeling for that, if the Earth went in front of the Sun, the Earth is about 1% of the Sun's diameter, so it blocks out about 1 part in 10,000 of the Sun's light. So you need to measure the brightness of all these stars to that precision in order to pick up an Earth. And that is now possible, but just barely.
Thank you.
All right, so over the next couple of years, as more powerful telescopes come online, I'm assuming we'll be able to see smaller objects like Earth size and Mercury size. What size of objects exactly are the different telescopes going to enable, and what would that actually tell us that we can't already know with the current methods?
Well, it's just a matter of the size and how accurately you can measure the brightness. And so, I mean, it's a whole new unexplored territory because we really don't know what kinds of planets are going to be in that size range, smaller than the Earth. And those planets tend to be just the little leftover bits. They're the flecks of dust that get flicked around when the big ones undergo any kind of special event. And so it's certainly possible that they could be very different in other systems from our own. But we just don't know yet, so it's really hard to speculate.
Hi, my question is, earlier you had a graph showing our solar system and how all of the planets are on a flat plane,
Yes?
and how some of the hot Jupiters were knocked off of that plane by a violent event. Does that mean that most solar systems will have most of the material or most of the planets along that flat plane?
Most of the ones we've found so far are like that.
Okay.
But again, our knowledge is limited, so we can see the planets that go in front of their star. We can go a little bit beyond that. So in some cases, we see a planet go in front of the star, but then next time it doesn't go in front at quite the time we expect. Like it's a little bit irregular, a bit ahead of where we expect it, one orbit, and a bit behind the next. And from that, we can work out there must be another planet. And we can work out roughly where it should be. It's a little bit off the plane, so it doesn't go across the face of the star. We can work out how massive it must be to perturb the planet that we can see. So from that, you can get an idea about how many of those off-plane planets there may be.
Okay.
And even when you include those, it still looks like the bulk of them are pretty close to all lying in a plane.
Do we know why most solar systems will form along that one plane and not have a whole bunch of planets that go a whole bunch of different axes?
Well, the simplest answer is probably the best there, and that is that if you take that cloud of dust and gas, it's supported by its rotation. It's basically in orbital motion around the star. So that supports it in the radial direction. But in the vertical direction, its rotation is not supporting it. It just has whatever pressure it has inside the gas to stop it from all collapsing to a thin sheet at the middle. That's why it's a disk instead of a sphere. It's thinner in that direction along the rotation axis. So if the planets form from that material, they have to more or less share the same rotation.
Okay.
They can scatter off each other a bit and push one up and one down a bit, but not very much.
Okay, thank you.
You had a remarkable image made by ALMA of in the millimeter wavelengths of a stellar disk, and I noticed a lot of radial structure apparent. Is that just an artifact, or is it something real?
Do you mean the various rings or something else?
The rays, the radial spokes coming out of it.
Well, so my friends who are radio experts tell me, so the ALMA telescope is not one big dish, but instead it has a few dozen smaller dishes that are combined to make an image. And you can combine them in slightly different ways, like weighting combinations of dishes close to the center versus ones that are further out. And I think it's possible to make those spokes go away. Not the rings. The rings stay no matter what you do. So we can't trust the spokes yet. In fact, people have done a thing where they try to wrap everything around, like lay the piece of the image that's at one angle on a piece that's at another angle, and they cannot find any convincing evidence for it not being perfectly symmetric, except for the fact that it's tilted over a little bit. So as far as we can tell, they're round rings and nothing more.
Good. Thanks for a great talk.
Thank you.
Hi, thank you for the lecture. I have two questions, actually. The first being is, given more to our solar system, the missing planet theory in our solar system, could you shed some light on that, given the mass of the planet that was supposedly in our solar system before it escaped and the apparent position it had in our solar system?
Well, you could imagine a couple of missing planets. So one would be inside Mercury. Why is there nothing there? And one answer that people have come up with in that case is perhaps there were some more planets inside Mercury and perhaps around Mercury's orbit, but they went unstable for some reason, and some of them collided. So Mercury is a bit unusual in that it has an enormous iron core and relatively thin layer of rock on the outside. And so perhaps what happened was some of those collisions blasted off whatever surface layers it had, and it's just the fragment that's left at the center. So that could be one explanation for why there's a missing planet very near the sun. Another possibility is that you could say there's a missing planet in the asteroid belt. Why do we have some small fragments that added up don't amount to anything even close to Mars, and not have another big planet? You could add a planet there and not much disturb the rest of the solar system. Various ideas have been put forward for that missing planet over the years. One is that perhaps Jupiter came inwards a little bit early in the solar system's history, and then went back out again, perhaps under the influence of Saturn as Saturn was forming. And if it did that, it may have cleared out the asteroid belt region, and may have also contributed to Mars being not that big. Mars is only about 1/10 the mass of the Earth. And so this is called the grand tack scenario, like a boat tacking in and then out again. So that might be an explanation for another gap in the solar system.
My second question is, are all Jupiter-sized planets that migrate into their parent star doomed, or are they able to theoretically stop in a position, say, like in the Goldilocks zone of Earth?
That is a good question, and one that many astronomers have been asking. So because we do see some hot Jupiters, they can't all plunge into their stars. And one way that they could stop is perhaps in the later stages of planet formation, as you come close to the star, there may be a gap. So the gas comes to an end. Perhaps it gets funneled onto the very strong magnetic fields of the sun when it's young, and then the gas goes along the magnetic fields and onto the star's surface. So in the plane where the planets are orbiting, there might be no gas. So perhaps if the forces from the gas stop there, at least there's no more gas inside the planet, perhaps its migration could stop at that point or near that point. That's one of the explanations people have put forward.
If I could just squeak one more in. Have you discovered any planets around A or O type stars?
Let me think. So I think somebody may have claimed an O star, but I'm not sure I believe it. But for A stars, there are quite a few. So what people have done is look at so-called retired A stars. So A stars that have gotten late enough in their life so that their outer layers swell up. So I should fill in there. So when A stars are in the main part of their lives, just like the sun, their outer layers are hot enough so that most atoms have lost enough electrons so that they don't produce spectral lines. And that means that you can't accurately measure the velocity of the star towards you or away from you. So for the main sequence A stars, we don't really know whether they have planets. When they get older and their outer layers swell up and cool off, they get the spectral lines back again. And so we can see the planets then. And so for those older stars, there are quite a few planets known. And I guess I haven't been reading up on that lately, but I think the last I remember, it looked like there was a deficit of planets in close. They started at about the Earth's distance from the sun. So they seem to be a little bit different than the sun-like stars in their population of planets.
Thank you.
Thank you.
Hi, thank you for a great talk. So we know that nebulae contain regions of dense gas and dust. So one of the theories is that a nearby supernova releases some kind of a shock wave that then bumps up against that dense region of gas and dust and triggering star formation.
Yes.
Can you shed some light as to how that happens? I've thought about it a lot. I'm still having a little bit of a tough time with the physics of how that occurs.
Well, seems like a couple of times a year somebody claims to have observed that in action, but it has been difficult to confirm. I mean, in one of these clouds, it's going to form a star and its planets. The outer layers can be quiescent when the inner layers have already begun to collapse, and so if we see a system over which a shock wave has just passed, it's a little hard to know if the collapse to form a star was triggered by the shock wave or not. Another reason that that's a hard problem is that we only get a snapshot, because the passage of the shock wave can take many years, many astronomers' lifetimes, and so we can't we can't get the whole picture. We just see an instant in time. And for those reasons, while it seems like a really plausible idea, and it may happen, I don't think it's been very convincingly shown that it is happening in any one particular case.
Okay, thank you.
Thank you.
I wanted to ask about the size of the star and what effect it might have on the potential planets that might form, the types of planets, the proximity.
So the size of the star. So people have been searching for planets around stars with a range of masses. We talked just a minute ago about the ones a bit more massive than the Sun. People have also looked at stars less massive than the Sun. So M dwarfs and even brown dwarfs. And there have been these disks found, so disks of gas and dust around the young examples. Many of those are known. Planets, I think there are fewer, but there are some now. I think there was a prediction that there should be fewer giant planets around the smallest stars, perhaps because you just don't have enough material. And I'm not sure whether that has been borne out in the planets that people have looked for. Of course, most people are looking for Earths, because that feels like the most exciting thing. And so there are fewer people looking at these smaller stars, and so we don't know as much.
Is there a tapering off maybe of the maybe larger and larger stars compared to the Sun?
So for we only know up to about the A stars, and there I don't think that there are significantly fewer planets, but just that they happen to be a little bit further out than for the Sun-like stars.
Thanks.
How do the stars and planets from other galaxies affect us?
We know almost nothing, unfortunately, about the planets in other galaxies. So almost all of the planets that we know of around other stars are within a couple of thousand light years of us, so within our region of the galaxy. Microlensing, which I mentioned earlier in the question time, there we can see planets just for a moment as they pass across a distant star. We can see planets that are halfway to the center of our galaxy. But planets that are further away, we don't have a good way to detect yet.
And I have another question.
Sure.
How are the planets formed? Like, are their sizes and shapes formed based on the size of the star and what type of star it is?
Let me see if I can add anything. So we talked a little bit about the A stars, in addition to the Sun-like stars, and then the low-mass ones. It does seem like there's a gradient in the size of the planets that you can form, and perhaps in how far out they are from the star. I think I can add a little bit to that. So if we look at the debris that's left over after the gas has cleared, so in our own solar system, the asteroids and comets are releasing dust all the time into the solar system, and so we have the zodiacal light, which you can see if you go out at a very dark site and look near the horizon just around sunset or sunrise. There's a little bit of dust floating around near the plane of the planets. And in some other planetary systems, we see that dust also, debris from the planets grinding and asteroids grinding each other down. And it does seem that around the lowest mass stars, we don't see that dust, except in one or two exceptional cases. So there may be something different about the environment there. So one idea that has been suggested is that the stellar wind, the winds from those low-mass stars, are able to blow out the dust, and so perhaps the dust is being produced there. Perhaps there are still planets, but we don't see the dust because it's been removed. So that's another difference in the planets around stars of different sizes.
Okay, thank you.
Thank you.
Tough view from the internet. There you go, sir.
Thank you. So I've been given some questions from social media. So Daniel Young T3 asks, what types of signals or cycles can we detect from exoplanets that we could not detect before? I would like to take this in a slightly different direction. So a signal that people have been looking for is the radio signals perhaps produced directly by planets. So Jupiter, as it interacts with, as its magnetic field in particular interacts with the solar wind, produces long wavelength radio emission, decameter wavelengths, I think, so many yards. And people have suggested that if you scale up Jupiter to a hot Jupiter, which is much closer to its star, so it's embedded in a much stronger stellar wind, and if it's young, may also have a stronger magnetic field, so it could produce really strong long wavelength radio emission. So there are some people here at JPL working with colleagues in India that have a big radio telescope that have been searching for that. I think some people at Caltech have also started a search, but nothing has been found yet. So, but that's an example of a signal that we've been looking for and hope to detect soon. Also on social media, Ian Mallett asks, could the reason that we're seeing more planets near stars be observational bias? Absolutely. It's almost all observational bias. Not entirely, because we've seen kinds of planetary systems that we just don't have in our own case. So that is certainly telling us something completely new. But one of the problems that we face is not fooling ourselves, not thinking that all that we've seen so far is all that there is, because there's a lot more out there. There's a lot more further from the stars that we haven't seen and won't be able to see, perhaps until they've done at least one orbit. I mean, Saturn's orbital period is 30 years, so we might have to wait that long to see a Saturn using the radial velocity method. So people haven't even been looking for that long. So there's a lot more to be discovered, and that I hope will be discovered in the coming years. And then a third question from social media, Prometheus 256 asks, how would we detect planets around a far-flung, identical copy of our solar system? Would our planets need to be detected using the transit method? So, on the whole, yes. And so Jupiter you could probably detect by the radial velocity method if you're willing to wait one orbit or maybe two to be sure, so 12 years for Jupiter to go around the Sun. The other planets would be really tough, but if they transited, then you could detect them if you had technology similar to ours. But you'd have to be lucky again, because our solar system is not compact like those others. It's quite spread out. So if you have a planet very close to its star, you have a decent chance, if it has a random orientation, you have a decent chance that it'll be along your line of sight. But if it's very far away, there's many more possibilities for its orientation, and you have to be there's a much smaller probability, if things are random, that you will get it along your line of sight exactly. So for somebody to see our Jupiter from a nearby star is much less likely than for us to see a hot Jupiter. So there's only a small number of aliens looking at our solar system and seeing it through transits right now. So I think that's all I have from social media. So, but I'm still got energy and raring to go, so I'm happy to take more questions if people have them. So, but otherwise, thank you very much for your attention.